came from another planet with superpowers in his afro, powered by radiation and disco music. Black Megastar, something's going down at the disco. Don't worry about it, baby. Black Omega Star will be there. He's Black Omega Star.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. We got cosmic queries grab bag today. Chuck.
Hey, what's happening? Yeah, we got a grab bag.
You grabbed inside the bag?
I did. It sounded. Sometimes they let you do that.
Stop. So let's go right in.
Yeah, we might as well jump right into it. This is Roger McVeigh, who says, hello, Dr. Tyson. Lord Nice. Roger from Wisconsin here, currently in Surin, Thailand. Wow.
Ooh.
Way to go, Roger.
Ooh, good food in Thailand.
Yeah, well, that's what I hear.
Eating.
He says, why is there not a lunar eclipse every month? Is it just the distance or the wobble or something else?
Great question. That's an observant question.
Yeah.
Very good. Very good. So if you look at the path the sun takes in the sky throughout the year.
Right.
Okay. So the sun actually moves against the background stars. You can't see the stars, but you can kind of see them at twilight, like before sunrise, but it's not so bright that you can't see the stars. Look at the stars that are there. They come back in a month. It's a different set of stars because I say the sun is moving. We are orbiting the sun, so our sight line on the sun is changing. Every month, the sun is in front of a different set of stars.
Right.
All right. That is called the ecliptic. The moon orbits in a plane that is tilted to the ecliptic.
Gotcha.
You can only get an eclipse if both the sun and the moon are in the same place.
Right.
In their tilted orbits.
Okay.
Okay? I'm just saying the sun has an orbit. I'm very pre-Copernican in this description.
Okay.
When they're in the same place, then Earth, the sun, and the moon line up.
Right.
But at any other time, the moon is above the sun, below the sun, or to the side, and it's got to be right. And it's called the ecliptic because when the sun, moon, and Earth line up, you get a eclipse.
Oh, gosh darn. That makes sense.
Doesn't it?
Yeah.
We good here?
Yeah.
So you can have a full moon, but it's not crossing the ecliptic.
Okay.
So it's not going to enter our shadow. Right. You can have a new moon and it's not crossing the ecliptic, and so it's not going to pass in front of the sun. You need a new moon or a full moon coinciding with when they cross the ecliptic.
Right.
And so that doesn't happen every month.
Right.
Not every month. And in Dune, was it Dune?
Okay.
Where there were eclipses every day. There's something getting eclipsed all the time.
I don't know which.
So it was not even interesting anymore because it was a kind of a daily phenomenon.
Yeah. It's like a sunrise at that point.
The sunrise, yeah. It's still fun, but it's not. You're not going to plan your life around observing it. Right. That's the simple reason. So if the two were aligned, we would have a.
If they were always in the same plane, it would happen that way.
Every month we'd have a total solar eclipse and a lunar. And the difference is, not that this was in the question, a solar eclipse, you have to be on the spot on Earth where moon shadow drags across Earth's surface. And if you're not in that spot, you're not going to see the eclipse.
Right.
Whereas in a lunar eclipse, the moon is entering Earth's shadow in space.
Right.
Anybody who can see the full moon will watch it enter Earth's shadow. The entire half of the Earth that faces the moon will see a lunar eclipse. Lunar eclipses are slightly, last I remember, it's slightly less common than solar eclipses, but everybody gets to see it.
Oh, that's cool.
You don't have to travel.
You don't have to go anywhere.
Very kind of the universe.
Yeah, it is. It is. Very cool, Roger.
Yeah, that's the only reason.
Eliseo says...
What? Spell it.
Elyssiel.
Okay, I don't know what you do with that.
I'm going with Eliseo.
This is a one-name person, like Cher, like Madonna?
Yes, exactly.
Okay.
Yeah, but it's like the more difficult version. See, Cher, Madonna, Eliseo. Salutations from Newcastle, Australia.
Love them.
Which, if it is the case that a black hole explodes at the end of its life, would that explosion contain all the energy the black hole ever sucked in, or has all that energy already escaped via Hawking radiation? And I wonder if the Big Bang could have possibly been an exploding black hole of such mass that the event horizon was larger than our observable universe. And the universe, as we know it, is now stretching out to fill the void left by the universally large black hole. Perhaps beyond is a far larger, far older galaxy that is pulling on the mass of our observable universe at great enough distance. It would seem that the pull attributed to dark energy. Thank you. So, did we get a black hole fart us out? And
is that the translation?
Basically. And then there's another galaxy that's older that is actually pulling on us. But what we're feeling is the gravity of that other galaxy. And that's why we think we have dark matter.
Got it.
Okay.
Couple things.
All right.
So he's right. As the black hole evaporates, it is losing mass.
Yes.
And the smaller the black hole becomes, the faster it evaporates.
Okay.
Until the rate at which it evaporates goes exponential. And in Stephen Hawking's original paper where he describes this, he says the very last gasp of the black hole will be of such high energy, it'll be a burst of gamma rays. Gamma rays. Because the wavelength of light is the size of the black hole emitting it.
Right.
Okay. So as the black hole gets smaller and smaller, the wavelength of light gets smaller and smaller. And that means it has higher and higher energy. Small wavelengths are higher energy. And so the very last gaps would be gamma rays. But that explosion means there's nothing left. So it's not like that's exploding and then you're filling the void with something that'll expand to fill that. No.
No, that was
gone.
it.
That's it.
That was the end of everything. Right.
It for the black hole.
Right.
So
it's spent.
Now, you want something outside our horizon, possibly pulling away, giving us the delusion that there's some mysterious force pressing outward on the universe. Right. The reason why that's not likely, nothing wrong with the idea coming in, all right? Somebody's tugging on it from the other side.
All right.
Because you're still, if that were the right explanation, it means you're still dealing with ordinary gravity.
Right.
Because that's ordinary gravity just pulling the other way. All right. And it wouldn't be a galaxy, it would be a whole other universe pulling. All right. The reason why it's probably not true is the dark energy is greatest the larger the region of space that you're describing. So it's not obvious to me why an external force of gravity would manifest that way here.
Right. So what you're saying is there are regions where it's greater than in other regions?
Well, it depends how big is the region that you carve. Right. That's all. So it's a property of the vacuum. Okay. So the more vacuum you have, the more of this you have.
Okay.
That's how you think about it. So that's how I should have said it. Yeah.
Okay. So the more, right.
All right. So as the universe gets bigger, this phenomenon is more significant.
Right.
Whereas if there's just something else pulling on the other side and we got bigger, the gravity would be less and less because we're getting farther and farther. Yeah. Right. So any and all ideas accepted, or considered, because we don't know what the hell dark energy is.
And that's what makes it so much fun that Eliseo can say this, because what I love is when our listeners think.
Yeah.
And they come up with these ideas, and it's real thinking.
It's real thinking.
It's scientifically based. It's really cool.
Yeah.
All right. But the answer is no.
Yeah, okay. All right.
All right, here we go. This is Paradox. Another one-name person. Just Paradox.
Paradox.
Yeah.
There's a wine called Paradox. but it has ducks on it.
Paradox?
Paradox.
Paradox.
Yeah, I think it's a play on that.
That's very funny.
Yeah.
I kind of, at first I was just like, man, I'm like, wait a minute, that's kind of cool. Oh, yeah.
I see what they did there,
That's
yeah.
a paradox. Okay, here, greetings, Dr. Tyson. This is Dennis from Salisbury, Indiana. The case for taking the word hole out of black hole. They are not holes in space. It's very off-putting to think of them that way. Renaming them could possibly give new perspective on them. BOS, Black Omega Star. How about that? He is upset that we call them black holes. They are not holes. And so the Black Omega Star, which sounds like a new Marvel character.
No, it sounds like the blaxploitation movie that was never made in 1970s.
Oh, that is right.
He came from another planet with superpowers in his afro. Powered by radiation and disco music. He's Black Omega Star. Black Omega Star! Something's going down at the disco!
Don't worry about it, baby. Black Omega Star will be there. Hold on for a second while I pick out my radioactive afro. Oh, shit.
So now I forgot the question. Could we rename it? I'm not one to debate word definitions.
Okay.
I'm not that guy. I'm not that guy.
I see.
Good words are good words. And if you have a good reason to think it should be different, I'll hear you out.
But see, don't they call it a black hole? Because when you look at it through a telescope, first of all, you see all the light of the universe.
Forget the light.
But I'm
call
saying
it black
like
hole because you fall in. You fall in.
Oh, that's true. You are falling in. You're falling in.
The difference is when we think of holes, we think of a two-dimensional surface and you fall through the hole.
Right.
This is a three-dimensional hole. Any direction you approach it,
you fall in.
It's a hole.
Right.
So that's a little freaky, but...
And by the way, when you fall in every direction then.
Every direction.
Because you're falling into a three-dimensional hole.
Yes.
So you got to be falling in every direction at the same time if you are falling in from any direction, right? When you get inside of it.
I don't know what you just said.
Neither do I. Who cares? Okay. It just makes sense that you're falling in every direction at the same time.
So it's a little odd that it's a hole in every direction, but so it's a three-dimensional hole. I mean, that's what it is. And light doesn't come out, so it's black. I think it's the best named thing there ever was.
Okay, well, that ends this conversation. Well, there you go. Sorry about that,
No,
Dennis.
but just think about it, because the word galaxy, you know what that comes from?
No.
It's Greek. Greek for galactose.
Galactose.
You know what galactose means?
Let me see. He's the arch nemesis of Black Omega Star. No, go ahead.
Galactose is milk. The Milky
Way.
This is how you get that.
Oh, that makes sense.
It's poetic and romantic,
It is.
but it's still, you have to go there. You got to construct what's going on.
Right.
And in China, where milk is a less popular beverage than in Europe, they don't call it the Milky Way. They call it the Silver River.
Oh, that's lovely.
That's way beautiful. For me, that's better.
That's even better.
That's better.
Sorry, Greeks.
And by the way, we found a sugar in milk, a couple of sugars in milk. One of them, we called it galactose.
Okay.
That's one of the sugars. And the other one is lactose.
Right.
Lactose, galactose. All because of the galaxy.
Right. That's cool.
Crossing our sky. Anyhow, so I think black hole is good, but Black Omega Star, that's
kind
again, it's the movie that was never written.
That's kind of wild, man. I kind of dig it.
Okay.
All right. Well, there you go, Dennis.
We get a phone call from some Hollywood director.
Exactly.
We got to make this movie.
Yes, Black Omega Star.
Radioactive afro. All right.
All right, here we go. Sam, I'm sorry. Oh, man. I'm thinking about Black Omega Star coming home from work and just, this woman is just like, where you been? Oh, you got time to be out there saving the universe, but you can't be in here taking care of these kids. Black Omega Star.
This is the home life.
Exactly.
The home life of a superhero.
You need to get your ass over there to them Black Omega dishes. That's what you need to do. All right, here we go.
Get you a black Omega ass on that lawnmower and mow the lawn. Take the garbage out.
Yep. All right, here we go. This is Sam Green.
Have you seen the Key and Peele skit?
On what?
Where they imitate me and my wife?
Yes.
You have seen that?
I did. I finally did see it.
Yeah.
Somebody showed it to me here, and it was very funny where...
Jordan Peele plays me.
Yes.
And I'm looking through a telescope, and and Keegan comes in dressed like my wife, and said, "Neil deGrasse Tyson, why don't you stop looking through that telescope and do the dishes and take the garbage out and walk the dog?" And then he says, "Well, in another universe, in a quantum ray, that's already happened. So, are we in this universe?" Or he says something really cosmic, and then she says, okay. So when I first met them, it was at the Emmys, because during one of our nominations when we had when StarTalk was on Nat Geo, and we were nominated for an Emmy 3 times.
Very nice.
They were there, and so I went up to him and said, "Dude, my wife has a PhD in mathematical physics, so the conversation would not have gone down that way."
Yeah, and then that's when Jordan Peele went, "Well, actually." You know, the universe operates on elegant principles, from quantum mechanics to cosmic evolution. But what happens when you want to explore the deeper questions that keep you up at night? Claude is the AI thinking partner for curious minds who love diving into complexity. Whether you're modeling stellar formation or exploring the intersection of physics and philosophy, Claude helps you dive deeper into the cosmic puzzles that fascinate you. Try Claude for free at claude.ai/StarTalk and see why the world's best problem solvers choose Claude as their thinking partner. All right, this is Sam Green. He says, "Hi, Dr. Tyson, Lord Nice. Sam here, living on Tulsa time."
Tulsa.
No, that's right.
Tulsa, Oklahoma. I rode in there's a river there in Tulsa.
Did not.
I rode there. That an annual festival.
Never been.
Yeah, when I was rode for the University of Texas.
Oh, very nice.
Yeah, beautiful town.
Okay.
That town has these big praying hands, I think.
They need it. Okay, he says, "My question is about space-time and causality. We usually limit our models of space-time to ones where causality is preserved. But I wonder, could space-time behave in a sort of meiotic or metodic way to preserve itself when causality is violated?" I realize I'm borrowing from biology here, but imagine space-time splitting when encountering...
Is that mitosis? M-E-I-T-O-S-I?
That's mitosis, yes. Mitosis.
Mitosis. What word is that?
He said meiotic, M-E-I-O-T-I-C, or...
Maybe he's borrowing from biology words, because I don't know that in physics.
Yeah, and then mitotic, which maybe that is the mitosis.
Okay, go on.
So I don't know either one of those words either. So maybe we can look them up, guys. Because, maybe I'm not even saying them right, to be honest. Who knows? I don't know.
People cut you slack every time now.
Well, listen, it's an honor to have me mispronounce your name or a word. All right,
that's you keep telling yourself saying. That.
He's like, "Come on, man, don't mess. Let that happen." All right, let's get back to him. He says, "I'm realizing I'm borrowing from biology here, but imagine space-time splitting when encountering a causal mass or replicating to contain a causal characteristics. Could such a mechanism
causal as in not causal.
Not causal. A as in not. Could such a mechanism be a way the universe maintains consistency?"
I like that idea. So the only way you're going to mess up causality is if you go back in time.
Right.
And Rich Gott wrote a whole, he's a friend of StarTalk.
Yes.
In fact, he's a co-author of mine.
Oh, cool.
We co-authored a book together called Welcome to the Universe.
Very nice.
It was based on a course that we co-taught together at Princeton, along with Michael Strauss, so the 3 of us.
Okay.
So it's Tyson, Strauss, Gott, G-O-T-T.
Nice.
I want to find that. And there were like 4 versions of the book. There's welcome to the universe. That's like textbook style. Then there's a brief welcome to the universe. That's like a pocket. Sorry. And then there's welcome to the universe in 3D.
Well, you guys really milked that thing, man. I'm telling you. Way to ride a horse.
All with Princeton University Press. So Rich Scott wrote a book called Time Travel in Einstein's Universe.
Right.
And there turns out there are solutions if you take a certain path around a black hole or a pair of black holes and then come back, you can come back before you left.
Oh.
There's a solution that I don't know how to calculate.
Okay.
But people who are fluent in this do. But we don't have to worry about the details of that. What we care about is the idea of it.
Right.
All right. Is the universe going to get angry if you manage to go back in time?
Mm-hmm.
Then tell yourself to not go back in time.
Right.
How you square that?
That would be the most awesome thing. I could see why the universe could get mad at that.
Right. So does the universe split? I mean, that's kind of what he's hinting.
Yeah, that's
here.
what he's saying. Because at that point, what you have done, because you already
you can't let that go.
You already went.
Right.
So when you come back and don't go again, what happened to the went? See? Because you already went. That's
Right.
how you got back.
Right.
But in the movies, what happens is you always end up doing something else that puts you right back where you got to go.
Or you disappear from the photo.
Right. Right. That's
Stephen Hawking has something called the time travel conjecture.
okay.
He thought that one day we would find a law of nature that explicitly says you cannot go backwards in time.
Okay.
And so as a conjecture, he's imagining that one day we will make such a discovery. You know what he did? He had a time travel party. Did you know about this?
I did not.
He or his people hosted a party at Caltech, and the announcement was made to all time travelers, come back in time and meet us here, and we will greet you. And nobody
showed up.
nobody showed up.
Yeah. That's funny.
So another one, you know, the one about the Titanic in the TV series Time Tunnel.
I don't know that.
It had the same producer. So it was a couple of shows that had the same kind of Land of the Giants, Time Tunnel. It was like 1 hour TV shows, primetime, that were science fiction-y. Okay. And Time Tunnel, the very first episode, they go back in time, and they're kind of lost in time. That's the show. They try to come back, and they can't. They land up in another place.
Oh, okay.
So where's the first place they went? The Titanic. It was the Titanic.
Well, that was the end of the series. Oh, well, that was nice while it lasted.
And so then the reveal is there as he's walking on the deck. Then he sees the lifesaver.
And it says USS Titanic.
Yeah. Well, no, it's not U.S. It's
that's right, because it's not the U.S.
It's British.
British, right.
Yeah, but I don't know. SS Titanic.
SS Titanic.
It's been hypothesized because everyone is so intrigued by the Titanic and that story.
Right.
That the day time travel actually gets invented, everyone wants to go back to the Titanic, and that's why it sank.
Yeah, well,
there wasn't enough boats for everybody because they're all time travelers.
I don't want to go back to the Titanic. I want to go back to a rowboat.
A rowboat? That's
sitting off to the side of the Titanic, and eating some popcorn. Like, wow, that is messed up. Look at that. You know,
who knows how that would get resolved? Either you can't go back in time, or if you do, the universe splits and prevents you from altering
one of the timelines.
One of the timelines, right. Correct. And and we're not there yet.
Right.
But it's a great question. Yeah.
Okay. Mm-hmm. That's super cool. Parker Mann says, hello, Dr. Tyson and Sir Charles. This is Parker Mann, retired geophysicist in Ventura, California. Now looking up instead of down.
Oh, nice. Mm-hmm. Tell me the name again.
This is Parker Mann.
Parker Mann. Yeah. Shout out to you.
Yeah.
All right. And by the way, we need more geologists to look up than down so that they will understand that it's one of our asteroids that took out the dinosaurs.
Mm-hmm.
Okay.
So
We got a whole lot of down-looking paleontologists out there. All right. I don't want to loop you in with the paleontologist, but Earth is your place. But yeah, all right.
he says, I recently saw a video in which Dr. Tyson said that Jupiter's orbit allows it to partially protect the Earth from asteroid impacts. If it were further out, would it protect Mars and closer in protect Venus? Can you elaborate on why Jupiter differentially protects planets based on its orbit? Thank you.
Good question.
Yeah, well.
Nice question. So we say protects Earth because we don't care if it protects Venus.
Anybody else. But the truth is, it's protecting everybody.
It's protecting everybody within its orbit.
Within its orbit, because
what would happen is
it's like a lineman.
A comet would come by, and you cannot escape the gravity of Jupiter.
Gravity of Jupiter.
I should say that more precisely.
Go ahead.
You cannot come in and out of the solar system without having felt the influence of Jupiter.
Nice.
Okay? Because the word escape has very precise meaning.
That's true.
And I don't want to say it that way.
Got you.
So, Jupiter is protecting Mercury, Venus, Earth, and Mars.
Yeah.
Period. So a comet comes in, it feels Jupiter, and then it swings out the other side.
Right.
It never even comes in.
Never even comes in to come towards us.
Correct.
Right.
So, plus, the distances between and among the planets is exponential. In units of the Earth-Sun distance, Mercury is 0.4, Venus is 0.7, Earth is 1.
Right.
One distance, okay?
Of course it would be.
Mars is 2.5.
Oh.
Jupiter is 5.
Oh.
Saturn is 10.
Oh.
Uranus is 20. Neptune is 30.
Okay.
But the distance is getting really big,
really
very
big,
fast.
very
That's
fast,
the point of this lame exercise I'm trying to lay down. And so all of the inner planets basically are huddled compared to where Jupiter is.
Right.
And its ability to protect its inner children. Yeah.
Oh, cool. Is that because the mass of these other planets is so much bigger that they need more distance so they're not disturbing?
They would clear out more distance.
They would clear out more distance.
They would clear out more distance.
Okay.
But the formation of solar systems is still an active field. Because we used to think any other star system would look like our solar system.
Right.
That's the first assumption. And none of them do.
Wow, that's so
Some
cool.
of them have Jupiters as close as Mercury is.
Oh.
They call hot Jupiters.
That's cool.
Yeah.
How you doing? I'm hot Jupiter. What's up, Saturn? That girl is ratchet. I'm telling you right now. All right, that's super
If you
cool.
want it, put a ring on it.
All right, Parker Man, what a great question. Here we go. Freddie Abden. Hey, Neil. Hey, Chuck. My name is Freddie Abden, an American living in Pereira, Colombia.
What's the name of the town?
Pereira.
I don't know that town.
I don't either.
Spell it. Maybe I do know it if you pronounced it right.
Pereira. Pereira.
Pereira.
Pereira.
Okay. It's an E-I-R-A? That sounds Portuguese.
Eira.
Yeah.
Pereira,
Portuguese, they
Colombia.
put the E in front of the I. Yeah, okay.
Where the best coffee is grown.
Ooh.
That's right.
Colombian coffee.
That's right. Colombian coffee.
We used to get those TV commercials.
That are known as cocaine.
Stop.
The second law of thermodynamics says entropy must increase. Yet, for a surprisingly long stretch, Earth maintained extraordinary order and complexity, enabling life to thrive in stark contrast to the decay and disorder we observed elsewhere in the cosmos. That should not have happened, statistically speaking. What could explain that rare pause in entropy, that bubble of low chaos? Could it point
Captain
to
Kirk? What could have explained?
Could it point to the unique initial conditions or maybe even some odd influence beyond our natural forces?
Religious people who know only some physics, but not enough physics, know about the second law of thermodynamics, that everything proceeds to chaos.
Correct.
That's a simplification, but basically it goes from order to disorder. Okay? And Earth goes from disorder to now we have like life. We can't get more complicated than life.
Right.
So they wanted to invoke that as a reason for not that physics didn't work, but that the hand of God intervened here, reversing what would otherwise be the trend that we see everywhere else in the universe. So it was not a statement of physics not working. It's a statement of the handiwork of God. And what is a miracle if not the suspension of the laws of physics? The proper way to say the second law of thermodynamics is for any closed system, the system will move to disorder.
Right.
Inexorably.
We're not a closed system.
We're open to the universe. We're open to sunlight.
Right.
We're bathed in sunlight. That is energy entering our system. Okay?
Right.
So if you have net energy flow into a system, then it's not a closed system.
All right.
So now, but you got to rob Peter to pay Paul. If our entropy is going down, life is lower entropy than what was there before, somebody's entropy had to go up.
Really?
The sun.
Oh,
the sun is dying. Yes, it is.
So that we might have life. A different kind of sun. Giving up life that we might live.
Oh, I see what you did there.
See what I did there?
I see what you did there. So the sun will die.
Right.
And then when the sun dies, nothing is bolstered after that.
Right.
And then the whole system
goes to entropy.
Yeah.
Look at that.
Now, a quick little aside, in our whole of the universe, we have a completely enclosed sphere, glass sphere, that has water and 3 life forms in it.
Why would you do that? That's terrible. That is just awful.
Okay. Yes, they're sealed in this cavity.
Oh my God.
All right. And so we have 3 life forms. There's krill, like really tiny krill.
Like the little shrimpy things.
Little shrimpy things.
Yeah.
We have snails.
Oh, yeah.
And we have something like kelp. Like an underwater
a plant.
Planty thing.
Plant.
That creates a complete ecosystem. Okay. So the krill poops, the snails eat the poop.
Right.
The thing, okay.
And then that fertilizes the kelp. And the sunlight comes in and helps the kelp.
Exactly.
And then it's full circle.
Oh, so you noticed it's not a completely closed system.
Right.
Because it's made of transparent glass.
Right.
So sunlight gets in. Okay, so now, here's the story. When we were building the Rose Center for Earth and Space in the year 1999, because we opened January 1st, 2000, there was a lot of construction dust. They finally moved that into place. And there's construction dust. So the construction people said, we clearly have to protect this sphere of glass. Up came the tarp.
Poor Snaily.
No, well, the plant. Yeah, I mean, so fortunately, clearer heads caught it. I mean, you can't blame the construction workers. I mean, they're not astrobiologists, okay?
They weren't looking at that like, guys, I know it looks like a closed system, but it isn't, okay? We got a lot of sunlight in. We need photosynthesis for the kelp. And the 2 life forms actually they're all 3 life forms and they're dependent upon each other. So, yeah.
I forgot how long. It was a few days, but you picked it up and there were a few belly up krill in there. But they reestablished their equilibrium and they're still going.
It's still going.
After 25 years.
In that seemingly closed
system. Seemingly closed
system.
It is living off of the sun.
Nice.
Yeah. So, yeah, that's how that works.
Okay. Very cool. All right. I love that. That was a great little lesson in entropy. Nicholas Hayes. Hello, Neil.
Oh, one other thing about entropy.
Go ahead.
Okay. You're alive, right?
We hope.
Okay.
Sometimes.
Right now you are consuming energy for being alive.
For being alive.
Where'd the energy come from?
I'm going to say Jesus. No.
That's the way you said that. That's very Southern Baptist.
But that's the only way.
Jesus.
Well, no. I mean, I ate food.
You ate food.
I ate food.
People say, they look at food and the calorie count is something bad.
Yeah.
The calories is the energy that you're using.
Right.
Do you know what the word for energy is in French?
No.
Calorie.
But the goes.
Okay, so when you die, you stop eating.
Right. Well, there's a reason why.
Sorry. You don't choose to stop eating when you die.
I see too many corpses like, God, I am so hungry. Man. Hey, why don't you eat? What are you doing, man? You're not taking care of yourself? Just because you're
Sorry,
dead.
I said it back. I'm sorry. I said it the wrong way. But when you're dead, there's no more metabolism in you.
Right.
Okay? And you begin to decay.
Right.
You become disorder.
You're moving to entropy.
Yes.
Right.
There it is.
Yeah.
Because you are now a closed system.
Right.
See, as long as you got a pie hole to shove food into, you're not a closed system.
Very cool.
Yeah.
All right. This is Nicholas Hayes. He says, hello, Neil and Chuck. My name is Nick, and I'm an industrial designer in North Bend, Washington.
Love him.
My question is, if I, in my super advanced starship, were traveling close to the speed of light and blew past a planet moving in the opposite direction, would I appear to be traveling faster than the speed of light to anyone watching me from the planet? Or would my reference frame constantly change based on what is being passed by?
Yeah, no.
Okay.
Next question.
All right.
No, so here's how it works. So at low speeds, you can just sort of add velocities. So if you're in a car going 60 miles an hour one way, a car going 60 miles an hour another way, you will pass each other at
120 miles an hour.
Thank you.
Yes.
120 miles an hour. Okay. What's really fun is in an airplane where you see the ground, going by slowly because you're high up, right? When another plane is coming towards you, in the opposite direction, the relative, because you're going maybe 500 miles an hour, and they're going 500 miles an hour, it's passing you at 1,000 miles an hour.
Mm.
If you want to see what like a supersonic jet would look like to you if you're just standing there, and it's
right.
It's really just check it out next time.
Yeah.
When you look out the window, you will find planes coming the other way.
Yeah.
And they go by fast.
Very fast. And they're pretty far away, and they're still zipping by you, man.
Zipping by.
Yeah.
So the formula to add velocities is very simple. It's this one plus that one, and that's your relative velocity. As you go faster, that formula breaks down. Really? And you need to use a relativity formula to add velocities.
Oh, please tell, because I'm not familiar with this.
You didn't know about that? Okay.
I do not know.
So,
this is so cool.
And the relativity formula, it is not how fast you're going. It's how fast you're going relative to the speed of light.
Aha.
And that ratio is in the formula.
Oh.
Okay.
Very cool.
Yeah, and so when that ratio is near zero, the formula just becomes two numbers added. But as the ratio gets higher, it's a more complicated formula. It becomes a more complicated formula. And so at half the speed of light and half the speed of light, you would see the other thing going maybe at 2/3 the speed of light, not because half and half would be a full speed of light.
Right.
Right? Going the other opposite directions. So if you're going 99% that way and 99% this way, you invoke the formula, you're never going to get higher than the speed of light.
Gotcha.
Yeah. So the answer is no.
Because if, let's say you were going, I don't know, 9/10 the speed of light, without the formula, you'd be going much faster than the speed of light when you pass each other.
Correct.
And you can't do that.
You can't do
so
that.
you can't violate that law.
Correct.
And so because you can't violate that principle of physics or the universe, you got to have this formula.
It's not just a can't, that's what we observe. And so this is the formula that describes what we observe.
What we're observing.
Right.
Gotcha.
The universe is not obeying our formulas.
Right. Yeah, that makes sense. Yeah, we've actually made a formula to tell us what the universe is doing.
Correct.
I got you.
And it's an important distinction.
It is. Yeah.
I will occasionally loosely say the planet is following Newton's laws.
Right.
No, Newton's laws are following the planet.
Right. Yeah, exactly. That's funny.
Yeah.
All right. That was no man. What a great question, Nicholas Hayes.
I can't recite it off the top of my head, but I'm sure there's a wiki page on adding relativistic velocities.
Relativistic velocities.
Adding relativistic. You just go there, and the formula has some squares and square roots in it. It's not complicated.
It ain't crazy.
It's not crazy.
Right.
Because we can go crazy if you want to go crazy. But so you can do it if you've had elementary algebra. Sorry.
This is John Stam. He says, "Hi, Neil and Chuck. This is John from Tampa, Florida. We describe space as being three-dimensional like a cube. Is the fabric of space better described as a four-dimensional or a tesseract because it is also expanding? What could happen if the universe stopped expanding? Would time or the speed of light be affected?"
We do not know what we measure is fundamentally linked to the expanding universe. It has been suggested that the second law of thermodynamics, since we just went in and out of that, might be a property of an expanding universe. And that if the universe slowed down and recollapsed, maybe isolated systems achieve order rather than disorder. Or does the second law of thermodynamics pass through an expanding and a collapsing universe? Do the laws of physics not change? So these are unknown questions. We make some assumptions, but they're not tested, and so we do not know. Our time dimension is not a space dimension. So it's not a tesseract.
Right.
Tesseract is 4D, 4 spatial dimensions.
Right.
And time is different. We need it as a coordinate, but it's not the same as the other coordinates because, as I've said, we are a prisoner of the present, forever transitioning between our inaccessible past and our unknowable future. So that is not a coordinate we can move back and forth on.
Right.
But X, Y, and Z, we can go forward and back, up and down, left, right. We have full access. So it's correct to say we live in 4 dimensions, but one of those is space. It's a very different world from one where 4 space dimensions exist, and then you have time on top of that. That would be the 5th dimension.
Oh, watch out.
Did I tell you the arranger of the 5th dimension was a family cousin?
Who?
The arranger. His name was Rene DeKnight. Rene DeKnight.
Oh, really?
Yeah. And every time the 5th dimension came through New York, we got tickets.
Oh, that's very cool.
I was a little kid, but the Ed Sullivan Theater, where they performed.
No, the 5th dimension is huge.
They're huge.
They were huge. They were worldwide. Like, when the moon is in the 7th house, and Jupiter aligns with Mars,
and peace.
I don't know the rest.
Will guide the planets, and love. I don't know how to sing. Love will steer the stars.
This is the dawning of the age of Aquarius.
5th dimension.
Yep. All right.
5th dimension.
Yep. All right. That was for all you Aquarians out there. We know how needy you are. All right. This is Marcus Gustafsson. Gustafsson.
Is it 2 Fs?
Yep.
Yeah.
No, 1 F.
One F.
Gustafsson.
Gustafsson. Okay.
Yeah.
Oh, is it 2 S's?
Yes.
Yeah. There you go.
Gustafsson.
I got the wrong double there.
Yeah.
Good.
He says, "Hello, everyone. Marcus here from Sweden."
You think? Gustafsson.
He says, "I have a question about the value of scientific understanding.
Love it. Love it.
I've always valued gaining knowledge about the universe after following StarTalk for years and reading books on the subject that I find my life has gained something for doing so. But I have a difficult..."
Notice he didn't say he read my books.
No.
He just said he read books. Just let the record show.
Okay. Yeah. I'm sure you're in there somewhere in his choices. He says, "But I have had a difficult time exactly pinpointing what. I believe I have gained scientific literacy, which comes with a different perspective on how to know what is true and the value of quantifying my ignorance, as well as getting humbled. What would you say are some more important things a person gains from scientific understanding, aside from knowledge alone?" Well, brother, you just named 2 huge things to learn.
Okay, so here it is. The number one thing is, the number one feature of science literacy,
Yeah?
it empowers you to know when someone else is full of shit.
Yeah.
It's empowerment. If someone says, "Oh, I have these crystals, rub them," and if you understand crystals and you understand medicine, you're not going to buy the crystal from the person.
Right.
All right? you are a victim of charlatans, which implies the person selling it to you knows better, or you're the victim of other people who themselves are victims. So he wants more out of this. Ain't that enough?
Yeah, I mean, and by the way, quantifying your ignorance is a huge self-awareness that most people never
Now,
ever
where
get.
I thought he was going with the question was,
What?
there are things that we can measure but don't understand.
Okay.
We measure dark matter.
Right.
We don't know what's
We don't know
causing
what
it.
it
We
is.
measure dark energy.
Right.
We don't know what's causing it.
Right.
We know we're alive. We don't know how we got from organic molecules to self-replicating life.
Right.
We don't know. Just because you can measure it doesn't mean you understand it. In fact, my favorite example here is once telescopes and cameras once film became sensitive enough to, if you look at any old photo, like from the 1920s, 1930s, somebody's blurred in it. Because the camera wasn't sensitive enough to light.
Yeah.
The film wasn't sensitive enough.
And you need long exposures
Long
for
exposure.
everything.
And they say, hold the position.
Right.
Okay. And there's always especially if it's a kid in a family photo, the kid is blurred.
Right.
It was very hard to get astro-worthy photographs because the image is very dim. When we did, we knew that when you take the starlight and pass it through a prism, you get important information about the light. Chemical composition. Well, there's features in the light. We didn't know. There's features in the light. There are bright lines and dark lines. It's a spectrum. In the 1910s and 20s, we started taking spectra of stars, knowing that one day that's going to be important, even though we don't understand it.
Right.
Okay? Even though we don't really know what's going on.
Super cool.
And so huge data sets came down the pipe. And we have laboratory counterparts to the spectrum. So we think that's hydrogen. Oh, we think that's carbon. We think because it's over here and we see it there.
Right.
And
That's, unbelievable.
no, it's amazing.
Yeah,
it's
just
amazing.
so great.
And finally the 1920s come along. Quantum physics gets developed. We understand the freaking atom, what electrons are doing, what they do to light if white light passes through it or any kind of light passes through it. And all the data we had been collecting and not understanding what the hell it was telling us became the foundations for our understanding of stellar evolution. And it's one of the great triumphs of 20th century astrophysics.
Wow. Yeah, man. That is very, very cool. All right. This is Alejandro Guardado.
That's a different Alejandro.
It is.
We had an Alejandro
Reynoso.
Reynoso.
That's right. Alejandro Reynoso.
And this one is
Alejandro Guardado.
Godardo. Okay.
Yes.
He coming in from where?
Alejandro from Washington State.
At least the other Alejandro was from Monterrey, Mexico.
Yes, Monterrey, Mexico.
Wasn't he from Mexico?
Yes, he was
from Mexico.
Mexico.
Okay, so maybe it's just Alex. They call him.
You can call me Alex, though. Hey, guys.
What you doing? Can I join?
Hey, got a question for you, dudes.
The uncoolest person in the room. You go from the most interesting man in the world,
Right.
to
Right. Hey, call me Alex.
okay, Alejandro from Washington State. What do you
Washington
have?
State. He says, "I'm a new Patreon member."
Oh, nice. Well, welcome
Thanks,
to the.
buddy.
I got to do my voice. Welcome to the universe.
There you go.
Oh, yeah.
You've been officially birthed into our family, bro.
And by the way, I think you do get a lower voice than me, but you don't sustain it.
I
You
can't.
have that whiskey voice.
That's why I can't sustain it.
Oh.
Because I'm drunk right now. He says, my question is, what are good ways to wrap your head around partial or even complete vacuums, for example, space? I am still trying to wrap my head around fans not working in space, and and I'm wondering.
That's a weird thought.
It is. Why don't fans work in space? And I'm wondering why these.
The rotor's spinning. I can't.
Oh, it's so still hot. I don't understand how I'm hot and it's only like 3 degrees Kelvin in here. Anyway, He says, I'm wondering why these things work the way they do. What is the vacuum of space? I mean, that's a very weird, like...
There's a deeper question there.
Go ahead.
And it's, what is nothing?
What is nothing? Yeah.
The best vacuum we've ever created was in the detector, was it, of the Large Hadron Collider.
Oh, cool.
Because you don't want those particles hitting stuff they don't want them to hit.
That's right. No, you got to suck everything out of there, man.
And one of the problems is material. I did this when I was in college. I worked at Bell Labs for one summer, and we explored different vacuums because we were testing for superconducting materials, and you want a very sort of pristine environment for that. But anyhow, so we have a cavity, and you suck out all the gas until the pump can't pump out any more out. You say, that's pretty good. Here's what you do next. You heat the walls. They're gas particles that got stuck in the texture of the surface of the cavity. You heat the walls. They all jump out. You see the pressure go back up just by heating it. Then you suck that out. Now you cool it down, and then you have a way better vacuum than you otherwise would have. But still, the particles left over there. So we do okay with our vacuums. You leave our atmosphere very far between the planets. That's an even better vacuum. You go outside the solar system between the stars. That's an even better vacuum. You go outside the galaxy between the galaxies. That's an even better vacuum. And last I ran the numbers on that vacuum has one particle every cubic meter.
That's correct. And you're one particle.
Yeah, one particle per cubic meter. So leave your fan at home. That's the lesson here. But if you take away that particle, then what is that? Is there nothing there? No, there is still something there. The laws of physics are still there. If you want a place where there's nothing, shouldn't you be removing the laws of physics as well?
Now we're talking like we're outside of matrix stuff now. That's,
all right, let me not even get there yet.
That's not even a loading program anymore.
Let's not even get there yet. Now there's no particles there.
Okay.
There is light passing through it. The cosmic microwave background visiting the region.
Right.
Okay. And there's something called virtual particles
that
popping in and out of existence. Quantum physics dictates this. And so there's a vacuum of no regular particles, but other stuff is happening. And through that volume is the fabric of space and time. So a real vacuum should have not only no particles, it should have no virtual particles. It should not even have a space-time continuum. And if it doesn't even have that, maybe that's how you get rid of the laws of physics. You took away the space-time. Maybe laws of physics are a part of space-time. So, yeah, this is kind of stuff you like over a beer,
Yeah, but make sure it's a 0-calorie beer.
No, I know I said beer because you would have said weed, right? That's a weed conversation. I never smoke, so I can't relate to what that might be.
That is definitely a weed conversation, man.
And by the way, and I forgot which one of my 2 Merlin books, they just got republished, one last year, and one is coming out in a few days, actually. Someone asked Merlin Merlin was my pen name for a column that I wrote for like 10 years.
Right.
And the public asks questions. So I'm very comfortable in this Q&A environment, just in case, I don't know, you didn't know that.
Well, we've been working together for a little while now, so I figured that out.
You figured that out? So one of the questions was, what's the best vacuum? And so Merlin is my pen name, goes through all the various vacuums.
Oh, really?
Yeah, and how many particles per cubic meter, there's a lot, and then less and less and less. And so it's in there and very cleanly described.
Very nice.
Yeah.
All right.
That's all the time we have.
All
my
right.
gosh. And all these were asked by Patreon members.
That's right. Thank you, all the Patreon people.
Yes.
We love our Patreon supporters. And you can go to patreon.com and join the StarTalk family for as little as $5 a month. You too can save a comedian. In the arms of an angel.
You need puppy eyes.
Yeah, no.
You gotta be looking through a gate or something.
Yeah, we need a chain link fence right here. And I'm just like, all right.
No, that's not where the money goes to. It goes to experiments that we conduct to try to
It allows us to expand the show.
expand the show in ways that are not quite commercially viable yet.
Right. Yeah.
And work on it and get people's input. And so,
No, we appreciate you is the point.
That's right. And we got StarTalk Plus channel now
Yes,
in YouTube.
because of Patreon.
Yeah.
Because StarTalk Plus makes no money at all.
Not yet. We're working on it.
Well, yeah. I mean,
We're working on what
maybe
works
one
in
day,
there.
but
Yeah, we're working on it. Okay, that's it, Chuck.
Yeah, man.
Another episode.
A grab bag, baby.
StarTalk Grab Bag.
That's right.
All right. So this has been yet another episode of Cosmic Queries Grab Bag Edition. Chuck, always good to have you.
Always a pleasure.
All right. Neil deGrasse Tyson here, as always, bidding you to keep looking up.